Hello everyone. In today's class for session 7, we will understand one of the important topic which is called as particle in one-dimensional box, which is the simplest concept where the quantum mechanics is applied. The learning objectives of today's class is to describe the quantum mechanical particle in a one-dimensional box, to solve the problem for particle in one dimensional box, and to define the potential energy V, to solve the Schrodinger equation, and to define the wave function, that is eigenfunction, and the allowed energies or eigenvalues for the particle in one dimensional box. So a particle in one dimensional box is a fundamental quantum mechanical approximation describing the translational motion of a single particle confined inside an infinitely deep well from which the particle cannot escape. Okay, so what is a particle in one dimensional box? It is the quantum mechanical approximation to describe the single particle motion confined inside an infinitely deeper well from which it cannot escape. Okay, now to understand this concept, the particle in a one dimensional box, it is a common application of quantum mechanical model to a very simple system consisting of a particle moving horizontally within an infinitely deep well from which it cannot escape, and the solutions to the problem give the possible values of energy, that is eigenvalue, and the wave function, that is eigenfunction, that the particle can possess. Now, the allowed energies and the eigenfunction which can squared gives the probability of locating the particle at a certain position within the box. Okay, so the square of the wave function gives the probability. And to solve the problem of particle in one dimensional box, what we have to do is we have to define the potential energy, and we have to solve the Schrodinger equation, and we have to define the wave function, and we have to find out the allowed energies for the particle in one dimensional box after solving the Schrodinger equation. Now first we have to define the potential energy. So let us consider a particle of mass m confined within a one-dimensional box as shown in the figure. The height of the potential well is infinitely height and the width is L. Okay, so it is made up of impenetrable walls. Such a system is called as one-dimensional box because the particle can move only along horizontal direction from x is equal to 0 to x is equal to L and vice versa. Okay, inside the box the particle is free but experiences a sudden large force directed towards the origin as it reaches the point x is equal to 0 and x is equal to L. It means that the particle exists only within the box and outside the box it cannot exist. Therefore, the potential energy for this problem at boundary conditions means at x is equal to 0 and at x is equal to L. So V becomes is equal to 0 for 0 less than x less than L, and V becomes infinity after the x is greater than 0 which is greater than L. So therefore the boundary conditions for the wave function psi is equal to 0 for x is equal to 0, and psi is equal to 0 for x is equal to L. What is the meaning of this? The meaning of this is the particle can exist only within the box because at the boundary conditions, means at the wall of the box, x is equal to 0 and at x is equal to L, the wave function becomes equal to 0. Okay, so the potential energy is 0 inside the box. V is equal to 0 for x is greater than 0 less than L, and it goes to infinity at the walls of the box, that is V is equal to infinity for x less than 0 and x greater than L. Okay, so if the values of x are lesser than 0 and greater than L, the value of potential energy becomes infinity. So we assume that the walls have infinite potential energy to ensure that the particle has zero probability of being at the walls or outside the box. Okay, you must remember equation 1 for V and expression for psi is equal to 0 at x is equal to 0 and x is equal to L. These two things you should remember. Next is to solve the Schrodinger equation. Now, the time-independent Schrodinger equation for the particle of mass m moving in one direction with energy E is minus h cross square by 2m d square psi by dx square plus vx psi x is equal to 0. Okay, so here h cross is a reduced Planck constant is equal to h by 2 pi. M is the mass of particle and psi is a stationary time independent wave function, and Vx is a potential energy as a function of position, and E is the energy. So equation 1 can be modified for a particle of mass m free to move parallel to x-axis with zero potential energy, resulting in quantum mechanical description of the free motion in one dimension. So that is given by minus h cross square by 2m d square psi by dx square is equal to E psi. It is because in equation 1 V is equal to 0 within the box. Okay. The equation 2 can be written as d square psi by dx square plus 8 pi square m E by h square is equal to 0 because h cross is equal to h by 2 pi. Upon simplifying, you will get d square psi by dx square plus 8 pi square m E by h square is equal to 0. That is equation 2. Now, the equation 2 is well studied and gives a general solution as for psi, that is psi of x is equal to a sin kx plus b cos kx, where a, b and k are constants. Okay. The third step is to define the wave function. So what we have done in our previous steps, so in the first step, we have defined the potential energy and boundary conditions. In the second step, we have solved the Schrodinger equation and we have obtained a general solution for psi as psi of x is equal to a sin kx plus b cos kx. In the next step, we have to define the wave function. Okay. Now, the solution to the Schrodinger equation we found above is a general solution for one-dimensional system. We now need to apply our boundary conditions to find the solution to our particular system. According to the boundary conditions, the probability of finding particle at x is equal to 0 and at x is equal to L becomes 0. So when x is equal to 0, sine 0 is equal to 0 and cos 0 is equal to 1. Therefore, b must be equal to 0 to fulfill the boundary conditions. Okay, so if b is equal to 0, then only the boundary conditions can be applied in equation 3. Therefore, psi of x becomes equal to a sine kx because b is equal to 0. Now, to solve for k, differentiate the wave function with respect to x. We will get d psi by dx is equal to k a cos kx from equation 4, and differentiate wave function again with respect to x. We will get d square psi by dx square is equal to minus k square into a sine kx from equation 5. So d square psi by dx square is equal to minus k square a sine kx. This is equation 6. Now, since psi of x is equal to a sine kx, then d square psi by dx square is equal to minus k square into psi from equation 6. Okay, and equation 4. So from equation 4, psi is equal to a sine kx. It is here in equation 6. So therefore d square psi by dx square must be minus k square into psi. That is equation 7. Now if you solve for k by comparing with the Schrodinger equation, we find that k is equal to square root of 8 pi square me by h square. How did you get this equation? This is because d square psi by dx square plus 8 pi square me by h square is equal to 0. And you have to compare this equation with the equation d square psi by dx square plus k square psi is equal to 0. So therefore obviously k square is equal to 8 pi square me by h square, or k is equal to square root of 8 pi square me by h square. So this is by equation 7 and the equation for Schrodinger equation. So now substitute for k. What you will going to get? The wave function psi is equal to a sine kx. We know that, right? So therefore, by substituting for k, we will get psi of x is equal to a sine square root of 8 pi square me by h square into x. Now what you obtained here from equation 9? From equation 9, it gives the expression for the wave function. So now we have achieved the eigenfunction for the particle in one-dimensional box, that is equation 9. The next step is to solve for A. To determine A, we have to apply the boundary conditions. Again, to recall the probability of finding particle at x is equal to 0 or x is equal to L is 0. So therefore, psi of x is equal to a sine square root of 8 pi square me by h square into x. When x is equal to L, we will have 0, means probability of finding particle, I mean the wave function psi becomes 0 at x is equal to L. Therefore 0 is equal to a sine square root of 8 pi square me by h square into L. So therefore you can see that the equation 10 is true only when the 8 pi square me by h square to the power half into L is equal to n pi. Okay, so therefore what happens to equation 9? Now square root of 8 pi square me by h square into L is equal to n pi, right? So therefore equation 9 becomes psi of x is equal to a sine n pi by L into x, because Square root of 8 pi square m e by h square is equal to n pi by L. Okay, so this is the simplified expression for the wave function. Now, to determine the value of A, what we have to do is the total probability of finding particle inside the box is unity. It means that there is no probability of finding particle outside the box. So when we find the probability and set it as equal to 1, we are normalizing the wave function. Okay, so therefore integration of 0 to L psi square dx is equal to 1. Therefore, what is psi? Psi is equal to a sine n pi by L into x. So therefore psi square becomes a square into integration of 0 to L sine square n pi x by L into dx is equal to 1. So therefore, from this equation number 14, the value of A becomes equal to square root of 2 by L. Okay. Therefore, by substituting for A in the equation for wave function, we get psi of x is equal to square root of 2 by L into sine n pi by L into x. So this is the equation for wave function including the value of A. Now to determine the allowed energies, so you have the equation for energy that is given by En is equal to n square h square by 8 ml square. From where did you get this equation? You will get this equation from equation 11. Okay, 8 pi square m e by h square to the power half into L is equal to n pi. By simplifying this equation, you will get E is equal to n square h square by 8 ml square. Now, from this equation 17, you will come to some important results. It says that the energy of the particle is quantized inside the box, that is inside the particle in one dimensional box. It means the energy can be discrete for the particle inside the box. The lowest possible energy for a particle is not zero. Okay, so En consists of the principal quantum number n, that is n square h square by 8 ml square. So n can have only the values 1, 2, 3, 4, etc. Therefore, the first thing is it is quantized, and the second thing is the lowest possible energy is not 0, because when n is equal to 1, E becomes h square by 8 ml square. Now, the square of the wave function is related to the probability of finding the particle in a specific position for a given energy level. The probability changes with increasing the energy of particle and depends on the position in the box. And the last thing is, in classical physics, the probability of finding particle is independent of energy and the same to all points in the box. Now, if you look at the wave function and the energy level diagram, it is shown in the figure. So you can see that the first energy level for n is equal to 1, E is equal to h square by 8 ml square. And similarly for n is equal to 2, you will get 4h square by 8 ml square. And similarly for n is equal to 3, you will get 9h square by 8 ml square, and so on. And the first image shows here, that is image A, is corresponding to the wave function of the particle in one dimensional box, corresponding to the values of n is equal to 1, 2, 3, and so on. Now, the wave function psi, that is psi 1, psi 2, psi 3, etc. is given by psi is equal to b sine n pi x by L, right? So psi 1 has 0 node, psi 2 has 1 node, psi 3 has 2 nodes, and psi 4 has 3 nodes for the particle in a one-dimensional box. And the probability of finding particle in a one-dimensional box corresponding to the different wave functions psi 1, psi 2, psi 3, etc. are shown in this figure. Okay, so you can go through these references to understand the particle in one-dimensional box concept. So we shall meet again in our next class.